When the block that we're looking at, or the object we're looking at, is mounted on a ramp or is sitting on a ramp, we have to do something a little different. The same basic ideas still apply. We're still going to draw a complete force diagram. Then we're going to look at the diagonal forces, any forces that aren't purely in the x direction or purely in the y direction. We're going to decide which those are. We're going to label them with the sine and cosine, x and y components, and solve them, and then see how that affects our equations. We're going to write net force in the x direction is 0, net force in the y direction is 0, and we're going to do that like we have on all the other problems. The difference, however, is that when we draw the force diagram, there's some things that are different about being on a ramp. First of all, the block would tend to slide down the ramp. We'll start with this one on the left. The block would tend to slide down the ramp, so friction must point upwards. Keep the block from sliding. Normal force, this one's been a little tricky for students. Find the surface of the ramp and draw a line directly perpendicular straight out of the ramp, just like that. So normal force, friction force, and Fg, the force of gravity. The force of gravity goes straight down. Notice that when we do that, that Fg is the one that's not lined up with everything. If I drew my x and y axis so that they line up with the normal force and the friction force, or the ramp, and perpendicular to the ramp, then Fg is the one that is no longer lined up with everything, and so we actually draw the triangle that we need for sine and cosine by starting here on the normal force, just come straight down, and that side is one of the components of gravity, and then I come perpendicular to the red line, perpendicular, so that makes a right angle. And so gravity, the full force of gravity here becomes the hypotenuse of this little triangle, not the ramp, but this little triangle with gravity on it. This side right here becomes Fgx. It's the one that's lined up with the x-axis. And this side right here becomes Fgy, the y-axis. The angle of the hill down here reappears up here on the triangle. Okay, if this, for example, if this was 20, this one right here would have to be 70, and this would have to be 20 again. So the angle that's down here at the bottom of the ramp appears here in the triangle with gravity as the upper corner. What that gives us is that Fgy is adjacent, and therefore would use cosine. Okay? And that Fgx would be opposite the angle and would therefore need the sine in order to figure it out. Following the pattern that we've seen in class several times, Fgy will be Fg, the hypotenuse, times the cosine of the angle down in the corner. In this little example I just said 20, so I'd put 20 in there. And Fgx will equal Fg sine of the angle. This stays the same no matter which direction we tilt the ramp. If I were to do it over here and tilt the ramp, I would draw my normal force right here. I would draw friction right here. The force of gravity would be pointing straight down again. And the force of gravity becomes the hypotenuse of the triangle. So again, lined up with the normal force, comes straight down, 90 degrees to that, so that makes a right angle. This line here is parallel to the x-axis. X and y are tilted this way now. Okay. This again is Fgy, and this is Fgx. Notice Fgy is still adjacent, so it's still cosine. Fgx is still opposite, so it is still sine. So all that stays the same. Okay, we do all those same things. The only difference is it's on a ramp, so the hypotenuse that we used was Fg, not one of the other forces. And that's really the only difference. Otherwise, it's the same as other questions or problems we've been looking at. Then we write the two equations. Net force in the x direction equals 0. Total x's equals 0. In the x direction, I've got friction and Fgx. Those are the only two. They have to add up and be equal to 0. And in the y direction, Okay, the sum of the forces in the y direction, the total of the forces in the y direction has to be 0. And again, if I look in the y direction up and down, I got Fn and Fgy. It doesn't matter which diagram I'm using, I get the same stuff. So no way on those, sorry, those add up to be 0 because we have constant velocity, which, right, could be moving or not moving, constant velocity. Using this information now, I can find Fgx and Fgy, plug them into the equations here, solve for friction and the normal force. And really, ramp problems, that's what they boil down to. They are that basic and simple at their beginning.